Okay, please keep in mind we are on Unit 4, and it is on momentum, impulse, and conservation of momentum. All right, so first things first, we covered momentum. So what that means is you have P equals mass times velocity. Okay, you can find that formula on page 6. It's pretty simple. They give you a mass, they give you velocity, whatever. Keep in mind, units for a impulse, excuse me, not an impulse, a momentum is kilogram meters per second. Okay. It's really not much about that. It's pretty straightforward. Okay. The second thing that we covered was impulse, which was the long formula J equals Ft equals the change in momentum equals mass times final velocity minus initial velocity. Because keep in mind, we said that only velocities change, so this is just another way to write delta V. I'm going to give you a hint. On your tests or any practice questions, I want you to notice that all of these guys have equal signs in between them. And what that means is I can say that Ft is equal to delta P. I can say that Ft is equal to m times Vf minus Vi. I can say that let's keep it in order. Ft equals J. Okay? If I go over here, I can say that, well, delta P is equal to J. I could say that delta P is equal to F times T. I could say that delta P is equal to M times Vf minus Vi. And then I can also say, and I'll use a different color, I'll use orange. I can say that M Vf minus Vi equals J. I can say M times Vf minus Vi equals Ft. And I can say that M times final velocity minus initial velocity equals delta P. Notice that all of these are the same thing, right? These are all the same thing. Everybody can be set equal to each other. So when you're doing a question, my recommendation to you would be, see what you have, pay attention to the wording. Okay, if they say force and time, I would circle it or highlight it, and then I would circle and highlight if they give you a mass and velocities. Okay, I just want to, wrong thing. I just want to know how you're going to see this written, this delta P. This is called a change in momentum. Momentum. That's how it's going to be written in the word question. So please keep in mind, you can have these forms of change in momentum equal to something that's equal to an impulse. So that means that delta P, because it is equal to an impulse, can have the units Newton seconds or kilogram meters per second. In fact, any of these guys, right, any of them can have those units over here, right, Newton seconds or kilogram meters per second. Okay, so like I said, you are just plugging in whatever variable you are given, and then you'll have absolutely no problem. Okay, remember we also spoke about the relationship when you guys saw this in your notes, right? So small force, big T, and then we had J equals big force times little t, right? You watched this idea in a video. This was the egg hitting the wall, and this was the egg hitting the sheet, right? And we know that when the egg hit the wall, it broke. When it hit the sheet, it didn't break. And the reason for that, and if you look at what I wrote, is because the sheet increased the amount of time that the force acted on the egg. The wall, on the other hand, that was a huge force in a small amount of time, which is exactly what our bodies experience if we didn't have an airbag, so most of us would die. But because we have an airbag, we actually see this idea happen where we are increasing the amount of time that the force acts on our bodies. Okay? Let's see. Also, another big deal is with the idea of momentum, right? And it was momentum versus mass and momentum versus velocity. Because both of these are in the numerator, right? It's always going to be big number over small number, which means that the other side of the equal sign is always going to be a big number. So when mass is doubled, so is my momentum. When my velocity is doubled, so is my momentum. Okay, so those are direct linear relationships. Also, another big deal, when we talk about impulse, right? J equals force times time, especially. This idea right here kind of comes from a combination of Newton's second law and third law. For instance, if I am like if I am a actually, you know what? Let's see. If I am a swimmer, right, and I'm kicking off the wall, right? Those are my legs. That's my arms, and that's my head. And I'm swimming, right? The amount of force that the wall pushes on me is the same amount of force that I exert on the wall, right? That's Newton's third law. Okay, so you might see questions that are talking about like an impulse, but keep in mind they're going to experience the same amount of force on one another, right? So if they experience the same amount of force for the same amount of time, that means an object's impulse is going to be the same. So again, if I'm a swimmer and I, you know, hit the wall of a pool with a certain amount of impulse, the amount of force that I'm experiencing is going to be the same amount of force that the wall's experiencing. Therefore, we're going to have the same impulse. Okay? And now, finally, we can review our, what do you call it? We can finally review our conservation of momentum. So, conservation of momentum. So we had elastic collisions, which is where objects bounce off one another. Most times where we usually see the another word, head-on collision, but for the most part we use this word bounce to tell us what's going on. If you do not see any of the other keywords that I will get into later in this video, that means you automatically have an elastic collision. Okay, and what that means is you have m1v1 plus m2v2 equals m1v1 plus m2v2. Oops, m2v2. So if you recall, when we draw a diagram, we do the before, we do the after. So I'm always going to have m1, v1, m2, v2, m1, m2, v2, v1. The arrows really don't make a difference because I'm just making this up on the spot. But if you notice, I am creating this equation right here from the basic idea of P equals mv, and because I have a before and I have an after. Okay, and how I differentiated with the subscripts, the 1 and 2, right here, so that means my velocity should have. So if I want momentum 1, I would say that's m1v1. Momentum 2 before the collision is m2v2. Same thing over here. Momentum after the collision is m1v1. Momentum of object 2 after the collision is m2v2. Okay? And then I'm just adding them, right? Because it's the momentum of both objects. Okay, again, we use that word bounce. Head-on collision tells us direction, so we really need to be mindful. So we do never eat sour watermelons. We know east is positive, west is negative. That's the typical directions that we like to see. Next you have inelastic collisions. Okay, so this is where we see that words interlock, stick together. Sometimes you'll even see move together. Okay, so keep in mind you have the before and the after. So before, these objects start out separated, some velocities, then after they get combined, so we have m1, m2, and they move with some final velocity together as one whole object. So again, we use the relationship P equals mv. So we have for momentum 1, we would have m1v1. For momentum 2, we'd have m2v2. So on this side, I would have m1v1 plus m2v2 equals, and now here our masses are combined, so we use the operation of addition. Oops, m2, and we multiply by the final velocity since they're moving together. Okay, so keep in mind this is also written as a form of P equals mv. So we would write this down here. Okay, that's your inelastic collision. And then finally, we have these things called explosions, which we primarily see for guns or cannons, and sometimes we see for springs too. That could sometimes be an example for you to see. So again, you're going to have a before, after. So, oops, this would be your M2, it's your M1. Remember when a bullet is in a gun or a cannonball is in a cannon, you know your initial velocity is going to be 0 meters per second. Once that gun or cannon is fired, they are now two separate objects. So you have M2, and actually let me label that. So I have M2, right? And then this is moving with some velocity. This is M1, and this velocity right here is actually called your recoil velocity. When we go to do the math, you, for the most part, are always going to see the object being fired towards the right side. It'll never be fired towards the left, because when you try to do your diagram, it'll end up being backwards math. So how we do this, again, we're using P equals mv. So here my masses are combined, so I say m1 v1, whoops. You combine the mass, so m1 plus m2 times vi equals, now you have two separate objects, so you're going to use the rule P equals mv. So I have m1 v1 plus m2 v2. Again, what I was saying was this velocity right here is known as your recoil velocity. That means you have the pushback, and for the most part, it is going to be going mostly towards the west. Please keep in mind that, what was I going to say? Oh, okay. So elastic momentum is conserved, energy is conserved, inelastic, P is conserved, but energy is not conserved because you're going to lose it. You're going to lose kinetic energy because it's going to convert into other forms of energy. And then your explosion, same thing. Momentum will be conserved, but energy is not conserved. Okay? On your reference table on page 6, you'll always have P before equals P after. A good way to check is to make sure that this number on the left side equals the number on the right side. If it doesn't, then you have a problem. You might have made a mistake somewhere, probably with the sign. Also, if you recall, I told you I was going to do these review questions. If you have a spring question and they give you two lengths, you need to subtract to find the change in distance or the change in elongation or displacement, whatever, or change in length of the spring. Okay, and then you can plug into Fs equals Kx. And then my second thing was linear acceleration versus centripetal acceleration. With uniform circular motion. Okay, Linear accelerations means that I am going to change my velocity. Okay, centripetal, keep in mind I'm going around a circle. When I see this term uniform circular motion, I need to know that v remains the same. So my speed remains the same, which means that I'm accelerating because I am changing direction as I go around the circular path. Okay, so centripetal acceleration, it's considered accelerating due to a change in direction. Okay, other than that, that's pretty much what you need to know for tomorrow. One last thing I will say though, keep this in mind, how we say P before equals P after. Sometimes they might say, well, what's this amount after the collision? And they'll only give you information prior to the collision. So like example, they'll only give you this information and they won't even give you anything on the other side where I'm highlighting over here. And they'll say, well, can you find P after? All you have to do is this math because we know the relationship P before has to equal P after. Okay, and vice versa. They might give you information all on the right side and no information on the left side. That's okay because we have this relationship on page 6. Okay, so please make use of your reference table. Know when it comes to drawing the diagrams, on your test, you have to draw them on the short answers. Like, that's not like an option here. And other than that, that's pretty much it. Just pay attention to direction, okay? And other than that, you'll be fine.